talk some work we've been doing in the context of software-defined networking, particularly in an effort to simplify how you go about building network optimization tasks in software-defined networks. This is joint work with my student Victor and my former student Vias. So let's first make sure we're all on the same page regarding what SDN is. So it's a kind of a new paradigm for managing networks that involves a centralized controller that manages a collection of switches. This controller runs a number of applications, here denoted by the letter A, right? Lots of applications. The applications are developed by a network operator or a network engineer, and they are informed by network data that's coming off of the control platform, the controller. Some examples of controllers are, for example, ONOS and Open Daylight, and we'll talk about those. Let's see if this is working. Does that work? Oh, yeah, it does. Okay, so, and one of the things we're trying to deal with in this work is the complexity of writing those applications, okay? So, generally speaking, right, you have a centralized controller that's going to configure a data plane of switches. In order to do that, it needs to sort of optimize certain goals for your network and ship out rules to the switches to cause them to do the right thing that is following that optimization, right? If the optimization says this switch needs to route this kind of traffic over there, then you need to ship out rules to get that to happen and so forth. And that's kind of the interaction between the control plane and the data plane. The applications are what's instructing the control plane about what kind of rules to be shipping. Now, again, by and large, writing these applications today is not easy. Right, Einstein up here has to consult his algorithms, textbooks, maybe call in his fellow researchers and so forth, use optimization tools to get this right, and that kind of thing. And what it's given rise to in the networking literature is a cottage industry of new optimizations to do different kinds of things. So this was our course attempt to try to categorize different flavors of research back from looking at the last few years of SIGCOMM and NSDI and related conferences, as well as some security conferences. There are people working on using SDN to implement traffic engineering policies, offloading policies that is moving sort of work out to data centers, service chaining, making sure that different classes of traffic traverse certain kinds of middle boxes so that they get treated in certain ways. There's a whole host of these things. In fact, the way we got into this work, this SNP stuff, is one of the things that we first did in this space. Basically, what we were trying to do is to get away from the perimeter defense notion of enforcing policy at the ingress points of a network, and instead pushing the enforcement into the network more pervasively, and in particular, potentially rerouting traffic to different places in the network where there's spare capacity to do policy enforcement. We had to do that, of course, without adding too much latency to the traffic. And so all of a sudden now we've got kind of some constraints that every type of traffic needs to be processed, or each class of traffic needs to be processed in certain ways. We need to get it to a place that has spare capacity to do so without adding too much latency. And so now we have something to optimize over. There's a whole bunch of these different things and with different goals. And so I'm not going to go into any of them in particular detail, but I just want to give you a sense that there's a lot of people working on different kinds of network optimizations here. Now, in general, to solve these things, there's a pretty standard recipe, okay, for doing it. And what it involves is, first of all, you sort of bone up on your theory of optimization and so forth, and get out your textbooks and think about how to do this. You try to formulate the problem that you want to solve, and then you try to throw it at a commercial solver, right? A Gurobi or a CPLEX or something like this. And then what you learn is that for the network you're working with and the kind of formulation you've come up with is just too slow, right? Oftentimes these are interlinear programs. They might be NP hards. You can't really make this thing go very fast. And so now you're kind of frustrated, and now you fall back and go, well, what are we going to do? And so you come up with some kind of custom heuristic, and you say, well, what if we try this? And by generating a custom heuristic, then you might get a fast answer that's somewhat suboptimal, but maybe it's close enough, more or less. And then, of course, you have to take the output of the optimization of this heuristic that you developed, and you need to map it into rules that an SDN switch can implement, which they're not particularly expressive in terms of what they can do. But nonetheless, right, you have to sort of find some way to do this mapping, push out rules to the switches, and get it to happen. So fair enough. That's what you kind of do today. And what we were hoping to do in this work is to simplify this process quite a bit. In particular, let's take Einstein out of the equation. Sorry, that's a bad pun. But let's take him, sort of put him on the side, and let's make this accessible to your average run-of-the-mill engineer, maybe even his boss, right? And so the idea is, can we come up with a way to simplify this process so that it's much more accessible and easy to write these kinds of applications? And to do that, we developed an optimization layer that sits between, it kind of sits underneath the application. So you write an application in the language of this optimization tool, and then you hit a big red button, and what it does is it does the optimization, figures it all out for you, generates the rules to ship out to the switches and pushes them out. And so kind of you have the one big, you've written down in a few lines of Python what it is you want to do, you push the big red button and your network gets configured. Right? That's the hope, anyway. So in particular, some of the things we wanted to do with this work is to not try to sort of force the application writer to come up with application-specific heuristics, right? We wanted to tackle this problem generically, but of course we have some limitations in terms of what we're going to be what we'll be able to achieve generically, and I'll talk about those in a few minutes. We wanted to, again, cause the application writer to focus on high-level network goals. And we wanted to allow them to sort of rapidly prototype and play with things. And think about an app being sort of 20 lines of Python, not hundreds of lines of C-plex optimization stuff, okay? So we want to make this really simple. And again, there's kind of a challenge in doing this, right? We would like to come up with things that are a sort of a general framework that produces fast solutions. Because a lot of these applications need responsiveness, not in the 10-minute time frame, but in the a few seconds time frame. And so we need to come up with a way to do this that would generate optimization solutions quickly. Of course, right, there were existing frameworks that could give you generality, but they couldn't give you efficiency. Similarly, there were heuristic custom solutions that would give you efficiency, but you couldn't generalize them. And so we're trying to sort of get the best of both worlds here. And what we came up with is something called SOL, which is an acronym for SDN Optimization Layer. Believe me, I implored my co-authors to not use this acronym, because for some of you, you might realize there's another meaning for SOL, or SOL, right? But they wouldn't go, they insisted that SOL was the right way to go. So here we are with SOL. And again, what this is this piece here that essentially takes in, it provides an API to the application developer that allows them to prototype these applications, and then sort of under the covers generates a formulation that you can give to C-plex or Gurobi or something like that, take the answers back that you get, the optimization solutions, and then configure the switches or generate the SDN switch rules that you can push out to your network. And in particular, SOL integrates currently with ONOS and Open Daylight, but there's really no fundamental reason it wouldn't integrate with others. Now, let's see. So one thing we want to do is accommodate a diverse set of applications, and so I'll talk a little more about that as we go. And I wanted to mention as well that this part is essentially logically centralized. The control platform is in charge of pushing the rules out to the distributed data plane. We're going to focus only on the centralized control part here. Okay, so the insight that we leveraged in building SOL was to use a path-based abstraction for allowing the application writer to write down what it is their policies were and their goals were. And so let me sort of walk you through how that works by looking at your classic max flow task. From your algorithms class back in grad school or undergrad days, right? So again, max flow is you have some sources and sinks and you want to push as much flow as possible through your network. Your edges have capacities and so forth. And if you look at the traditional way for expressing that, it's expressed in what I would call an edge-based formulation, whereby each of the edges has some capacity and you have some variable that accounts for how much flow gets pushed across each edge, and you have some conservation rules, like the flow across edge 1 has to equal the flow in via edge 1 has to equal the flow out via edges 3 and 4. Okay, so you have some conservation of flow rules around, or requirements around the problem. what we're going to do in this work is actually think about it from a different perspective, which is imagine every possible path that you would want to take through this network. And then you can sort of think about how much flow gets sent along each path. And then you can express some things like, well, you know, the flow that goes across all the paths between the source and the sink has to match the demand that's being placed there, or that's something like this. And so the reason that you don't think about it in those terms, right, the path-based way in your algorithms class, is because there's just a lot of paths. Okay, and so you get this exponential blow up, and that's not the right way to think about this problem, right? Well, that's kind of true, and so we'll see how we get around that in a few minutes. But what's nice about this path-based abstraction is it allows you to write policies about your traffic classes in a natural way, which is, would you be happy if that class of traffic took that path in your network, right? So for example, in this case, you might look at a class of traffic that's entering at node N1 and leaving at node N5. And you may have a requirement that that type of traffic needs to go through a firewall and then a proxy. Okay? And so we can write down easily now a little predicate that evaluates, given a path, whether you're happy with the traffic of this class having taken that path. And what it does is it tests, is there a firewall on the path? And if so, is it followed by a proxy? And if the answer is yes in both cases, we'll give it a thumbs up. Okay? We'll be happy with that path. And that the notion of a path policy is very natural for network administrators to be able to write down. And so what that means is that sort of we can, in terms of the interface to the network design, the network engineer, the network application writer, it's a natural way to think about writing down policies for this. So it kind of gives us some generality. Again, though, the trouble is that you've got a lot of paths. And so how are we going to deal with that in coming up with a way of optimizing problems expressed in this way? Of course, the trouble with having lots of paths is that when you try to generate all the right variables and so forth to feed to the solver, it gets huge, the solver slows down, and so it just doesn't go very fast. And so that leads to how we go about optimizing things. And the way to think about this is that we break up the solve pipeline, if you will, into 4 stages. The first one is path generation, where in an offline step, and the key thing here is this is offline in advance, right? You're given a specification for different traffic classes of what kind of paths they're allowed to traverse. And we generate through the network offline the paths that are policy compliant in this respect. And when it comes time in an online way, then to solve a particular optimization, we will downsample from the policy compliant paths in one of a few possible different ways to generate a handful of paths over which we do the actual optimization. And the reason that is helpful is because, of course, now we're working with a smaller number of paths. The natural question is how much optimality do we give up in doing this? We'll talk about that in a few minutes. But it allows us to produce optimization results very quickly. Once we do that, we then have to once we've fed it to the optimization tool, to do that, we have to sort of come up with a way of modeling the various constraints. We give it to the solver and solve it, and then we have a way of automatically producing rules that the SDN switches can implement that we push out to the switches. And so that's kind of the process now. So there's an offline phase followed by an online phase. Now, we built this. The source code's available. You can go download it. I'll give you the URL at the end of the talk. Basically, it's a Python library. And we've interfaced it with the CPlex solver and the ONOS controller. We have a very glitchy one that also works with Open Daylight. And we've prototyped a number of applications in various kind of vanilla ones like max flow and traffic engineering, latency minimization, but also a number of things that have been published in the literature. We've taken their problem statements and we have written them in our solve framework as a way to force us to exercise the tool to make sure that it's general enough to encompass what it is they wanted to do. And I'll give you very quickly, I'll give you sort of a sense for what the code looks like. This would be a way that you would write, say, max flow. Now, there's a little bit of preamble boilerplate stuff that I've left out, but by and large, you're looking at about 6 lines of code, okay, to write max flow. You've got a step where you specify the topology, right, to the optimization. So this is the network topology and the traffic classes. You also have some parameters here for for how you're going to downsample paths when it comes time to do the solution. And so this produces both an optimization object and a paths per traffic class object. Just skipping forward a little bit, there's a function here in line 3 that allows you to is used to compute the resource that you're primarily concerned with optimizing over. In this case, it's the number of bytes per second, say, that are part of a traffic class, right? And that traffic class might be web traffic entering here and leaving there, or something like this. There's basically a way that you specify link capacities and so forth in this language. And I know it looks very kind of arcane and so forth, but it's a fairly simple little interface. Then you basically say, look, I want to optimize for max flow, and I solve this thing, and this is the whole, and your network gets configured, essentially, to do this. You can easily change this to, say, do simple traffic engineering by requiring that you route all the flow, but minimize the total bandwidth, which would be a very classic kind of traffic engineering goal. Okay, so basically with small modifications, you can adapt existing things that you've done in this little language. Now, of course, when evaluating something like this, right, there's a number of questions, right? Have you actually saved the application developer much work? How fast can you make these optimizations go? And also, how much optimality are you sacrificing by doing things this way? Because we are using a heuristic, this downsampling of paths, to get it to go fast. And so I was going to talk through a little bit of each one of these. One of the hard things, of course, is how do you measure having saved developer efforts? And the best way we could come up with was to just look at the difference between the number of lines of code that you write with solve for a given application and our own implementations of these other applications that people have written, right? Well, in some cases, these aren't our own implementations. We actually got them from those authors. And what you see is that there's sort of an order of magnitude plus improvement in just the number of lines of code you're writing here. Now, that's not a great, first to admit, that's not a great measure of how hard it is to use a tool, but it's the only one we can think of, and maybe you guys have ideas for better ways of measuring this. I don't know. I'd love to hear them. The second question that we sort of set out to evaluate was how long does it take to produce answers? And so here are two representative examples. This is pretty typical for the kinds of things that we played with. What you see here are two graphs, each of whose x-axes are different network topologies. Okay, so things like Abilene and Quest and Giant 2012 and so forth are network topologies. In parentheses are the number of routers in those topologies. Okay, and what you see, these are the top graph is for an application called Panopticon. This one's another application called Simple. It doesn't really matter so much right now what those applications are. These are two published applications, not by ourselves, that are both kind of service chaining applications, right? So for each kind of class of traffic, you say, look, I need this class to go through a firewall and a proxy. I need a different class to go through, you know, a firewall, then an IDS, then a WAN optimizer. You know, you have all these sort of different chaining requirements about how you traverse different middle boxes in the network. And what we did is we implemented their own optimizations from their papers, and then we encoded the same problem in Sol. And we set them both running. We said, well, how long does each of them take? What I would encourage, or one thing I want to point out to you is that the y-axes are in log scale now. So what might look like a fairly small gap is actually a really big gap in runtime. And the shaded areas of these graphs are places where the original formulations of the problem wouldn't compute for us in under 30 minutes. So after 30 minutes, we called it off because by that point, of course, probably the results of the optimization wouldn't be useful anyway. But what you can see here is that Sol is giving you much faster optimization results. And in each case, the results that we were getting were less than 1% away from optimal. That is the actual optimal answer. Okay, so we were able to compute eventually the actual optimal answer. We were only about 1% off. This is a different view of the same kind of results, which is now carved in a different way. What you see here are four graphs. The top two are for Panopticon, the bottom two are for Simple. Now the network topology is indicated by the color of the line. And basically the x-axis represent the number of paths that you downsample to for each traffic class. So if you have a certain type of web traffic entering here and leaving there, maybe that's a traffic class. This would say, well, we will downsample to 5 paths, 5 policy compliant paths for that class of traffic, okay? Or maybe we downsample to 10 or to 15 or to 20, okay? So the number of paths. Obviously, if you allow all the paths in your optimization, you get the optimal answer. It just takes a long time. Whereas if you downsample to 5 paths, you get an answer very quickly, but you sacrifice something in optimality. The right side shows you what you sacrifice in optimality. And what this shows is that, in fact, a lot of these problems allow you to downsample really quite a bit, right? In this case, the optimality gap is only 1% across the board, even when you're using only 5 paths per class. Here, you pay about 5% with 5 paths per class, but as you move the number of paths per class up, right, to say 10 or 15, you quickly approach the optimal answer, okay? So, and again, right here you can see what you're paying in terms of time to solve that problem with that number of paths. So this gives you sort of a different view of the same data. Now, you might want to know, well, where, in terms of, if you look at sort of an end-to-end, you know, push the big red button, configure your network, sort of where is most of the cost? And this shows you for different, again, network topologies, where the cost is. In this case, this is for a simple traffic engineering application. So route everything and minimize the max link load, okay, kind of thing. And so what you see here, first the punchline is that to configure an entire network of 11 or 20 or 40 or however many nodes, right? Typically we're able to do this in under 15 seconds from pushing the big red button. And the time is spent somewhat in the optimization routine. Those are the blue parts of the bars. But the route installation, in terms of pushing out the rules, also constitutes a good chunk. That's the red part. The least, well, not always the least, but sometimes it's about the same as the red part, is the green stuff, which is basically just taking the optimization results and figuring out how to express those in rules that you can ship out. Okay, so that's another interesting sub-problem that I'm not going to really tell you about today. Let's see. One other thing I want to mention to you is for a lot of these applications, you have to periodically resolve and ship out new rules. And sometimes you need to do that pretty quickly because some event has happened that causes you to need to adjust your routes very quickly. For example, a link fault, right? So a danger, though, in doing this regeneration of the solution each time from scratch is that you'll cause your network to kind of lurch from one configuration to a completely different configuration in which you just moved where every flow is going, right? You had this posture, something failed, you resolved it, and it changed everything. And said, no, your traffic needs to do something completely different now. And that's really not a great way to run your network. And so one of the things we've extended with, solved with is something called a MinDiff piece that allows you to take in as an input what your previous current posture is, your current routes and so forth, and use that in the optimization goal to say, look, I want to weight not only optimality of the answer for, you know, minimizing the link load or whatever, but in addition, I want to equally weight, with equal priority, weight the goal of not changing everything, right? I don't want to cause my network to lurch like that. And so you can sort of use, you have a bi-criteria optimization problem now, right? Either you don't change or you do, right? You might need to change to get to optimal, but you don't really want to cause your network to lurch. So now you've got a balance, right? And so this just kind of shows what's happening. In this case, right, maybe this was your original setup where the darker lines are where more of your traffic is going. And then maybe you get link failure here between N2 and N4. And so one way that your solve could produce a new answer if you didn't do the MinDiff thing is it would say, look, I'm going to change where class C2 is going because I have to, right? That link is now gone. But it might also change where class C1 is going even though it didn't have to, just in order to optimize the goal. Instead, in the MinDiff setup, what we would do is we would try to keep, say, C1 where it is. Just move C2 because we have to, but we might sacrifice additional optimality because we didn't want to change everything. And so this gives you some sense for kind of how this plays out. I'm not going to go into this in too much detail. Again, network topologies are on the x-axis. What the y-axis is on this side is the traffic shift in terms of the percentage of traffic that ended up getting moved. And the blue bars indicate what happens with the MinDiff configuration in a particular weighting, and the green bars indicate what you would have moved had you actually just not cared about how much of the traffic you were sort of lurching around. And so obviously, right, with the MinDiff configuration, you get to not lurch as much, not move as much traffic, but you do pay something in terms of optimality because you weren't willing to move as much. In some cases, right, in some outlier cases, this can be quite substantial, like 20% plus. But if you look at the medians of the optimality gaps, right, you're sort of sacrificing typically less than 10% to save yourself from needing to move all of your traffic, okay, and how it's routed. So, okay, so in summary, today, if you look at programming SDN networks and applications, it takes quite a bit of expertise, right? You have to sort of, again, go back and dust off your algorithms, textbooks, and so forth to get this right. And what we're trying to do is make this a lot more accessible to your average network administrator. And so we've developed this code, right? You can go to this URL and download it and play with it. And what's neat about it is it allows you to write applications in very few lines of code and sort of push the big red button and get your network configured very quickly. And that's where we are right now. Any questions about this? Whoops. What just happened? Well, I guess nothing up there. Okay. Any questions? Yeah. Oh, thanks.
So I think it's very useful. I think I understand the speed up here coming from the path sampling.
Yeah.
Right. So I'm wondering if uniform sampling would make sense without knowing the objective function. Sometimes the objective function they really influence the way you do sampling.
Absolutely. So right now in Sol, basically we have very primitive sampling methods. So the application developer tells us, do we want to sort of bias that sampling towards shortest paths or random path selection? Obviously, latency sensitive apps, you'll tend to go towards shortest. If it's not latency sensitive, maybe randomization, just purely random from all the possible paths is okay. We're currently doing some work that tackles exactly that step more intelligently because I think there's a lot of advantage to be gained in doing so. And so that's something we're pushing on aggressively right now. But all the ones I showed you were using the primitive sampling techniques. Yeah.
Uniform kind of.
Yeah, it's either the shortest or it's random uniform. Yeah.
So then this is mostly toward traffic engineering kind of like security here. You cannot do even sampling because if I want to guarantee that there's no backdoor in any path, then you have no.
Well, but so the reason we can satisfy that is because. I'm thinking about this from a service chaining point of view. Okay, look, I want to only admit paths that go through the firewall and then hit this NIDS or something like this, right? We only allow paths that meet a predicate that the application developer specifies as part of the configuration of this thing. So they write a little Python routine which tests whatever they want to test about the path per traffic class, and they have to tell us what is policy compliant for that class of traffic. But if they give us a runnable function that says yes or no about that path for this class, we will only admit the ones that are allowed as policy compliant.
So you assume there's some configuration in the system already and you kind of optimize what you already have? Or you assume
yeah, that's right. We have to take as input some specification of policy for exactly the reason you point out, right? That we can't dream up what the policy is for a class of traffic. So the application developer has to tell us. And the way we ask them to tell us is to write a little Python routine that takes in traffic class and path and give us a yes or no, a binary answer, right? Yeah. Yes?
So, two things. One, you had a graph which, if you back up,
Here?
Yeah, so how come there's no decrease at all on the top?
Yeah, I know, right? So, in other words, to get for the Bell Canada topology, right, 48-node topology, to dent this below the 1% optimality gap, you have to go to a lot of possible paths in this particular case. But the good news is that at only 5 paths, you're already at 1%
Right, that's what I'm
optimality
wondering.
gap.
It's just such a simple topology that there's no.
You know, I mean, I honestly don't have the Bell Canada topology in my brain, so I wish I could.
What are the numbers in parentheses?
That's the number of routers in the topology.
Okay,
Yeah,
that's what's wrong.
that's right.
Yeah, okay. Let's see. Two other things. I guess so. It's nice to see that. I remember funding some of Nick's early work, and the rationale was being able to specify these paths, and that was the security aspect of it. Was that you could actually know where the traffic was going to go in a much more straightforward way. So
Right.
Is there any other security aspect to this?
Any other security aspects to it? Let's see. It's funny that you put it in those terms because in many respects we've been. I think one of the key insights in this is that what we started with as a security problem, right? Offloading network intrusion prevention systems, the SNPs work I mentioned earlier, to spare capacity in data centers, which we publish in security venues, and we thought we were very proud of ourselves, right? Hey, that's really cool. Once we took a step back and looked at what's happening in the SDN space, we realized that all these problems, whether it's topology reconfiguration to save energy, or spare capacity for network intrusion prevention or something else, or whatever, all these different categories of things are by and large the same problem, right? I mean, not really. They all induce their own customizations to the optimization that you need to do. But they're sufficiently simple that you can abstract away key elements, right? These paths and so forth, and derive optimizations automatically for them. And we actually, it's funny that you ask it in those terms, because we think this is a feature, not a bug, right? That this is I think one of the key things about science of security is finding the basic principles. And if it so happens that those principles apply to lots of problems that aren't purely security related, that's a thumbs up from my point of view, right? So, yeah. Yes.
Yeah, I guess the same kind of, I was trying to understand what the application beyond being able to understand what traffic is going through, what part of my infrastructure, which is certainly helpful in a security context. But can I get more kind of complex in what my policies would look like in terms of selecting, movement of particular kinds of traffic? So it's not just traffic type based, but perhaps there's other qualifiers that will cause me to redirect traffic down through a particular part of the infrastructure.
Yeah, so so one of in that big table I have, one of the pieces was called the dynamic service chaining. One of the little squares was dynamic service chaining. And what we mean by dynamic service chaining is that you don't know a priori what fraction of your traffic you're going to have to split off at a certain, say, NIDS or NIPS or something, right, to get analyzed somewhere else off the regular path for the good traffic. That would be an example of the kind of I think you're talking about. And so this is one of the things we're trying to figure out right now, is sort of how to extend this framework to be as robust as possible to a lack of knowledge of what fraction of that traffic you're going to encounter, right? So one of the things I mentioned to Ehab that we're focusing on is, well, let me not tie it directly into that, but yeah, so we're trying to look at how to be robust and responsive to unanticipated traffic characteristics, right, in the generation of the configurations that we're producing. And then to be as responsive as possible. One of the big things this helps with is when you get an anomalous traffic event, if you had to work from the original optimizations to reconfigure your network, it might take you a long time to respond, right? By pushing this down to sort of the few seconds time frame, you get much more responsiveness. So that's one piece that we already give you, but in addition, we're now trying to figure out what are things you can do in the path selection stage early on to be as robust as possible to unanticipated traffic demands of different types. Does that make sense?
Yeah, but it seems like, again, it's a traffic demand kind of optimization focus, as opposed to some state that the system becomes aware of that it considers to be, not ideal from say some kind of security policy standpoint. So I'm trying to understand the difference between an optimization problem with respect to the efficiency and balancing load to application of security policies and how do I optimize around those sorts of things.
Well, but so are you asking what? So are you thinking about what happens if the policy changes in the network, such that paths that traffic classes would take
would be different?
You'd be forced into a different set of paths,
Exactly.
right?
That's one potential.
Yeah. So that's not something we really handle right now. I guess I'd be interested to understand the scenario you're concerned with where you want to change the policy for your traffic without much forethought. Because that's kind of what you're pointing to is right now we've got to change policy, we've got to do it right now, right? We don't have time to generate the paths offline and so forth. To me that seems potentially dangerous, but maybe you have a scenario in mind that I'm not thinking of.
It's a good conversation.
Yeah, we should have this.
Yeah.
Okay. Yes.
So it looked like earlier you had a matrix of 12 to 14 different sort of optimization problems.
Right.
It sounded like you implemented 3 of those.
Let's see. Well, we've implemented how many have we actually? So my student Victor, you're talking about. There it was. My student Victor has implemented a number of them. I don't know how many are up on the site, the download site. So on the URL I gave you, there's a number of these examples there. I don't know how many.
I thought I had seen 3 at one point, and I was just curious whether there's a reason you hadn't done more of those issues with your generalized generalization of this problem.
So the thing is that each one of them, it takes a fair amount of effort to replicate each of them because you have to go understand the paper and their original formulation to make sure you get it right. And the cottage industry is very active, so it keeps growing and growing and growing. So there's no way we'll keep up with poor Victor being, trying to ingest all these papers and go convert them into this. Our hope by giving away the code was to allow people to play with this and see maybe we could get them to start prototyping their applications in this.
But you don't think there's any reason it wouldn't generalize all of them?
So I'm not going to say that everything we know about it will generalize to, but I think for the most part these we can do. But yeah, I mean it's now that I've said this and it's on tape, someone's going to come up with a paper that says but you can't do this, and then they'll probably be right. There's always going to be some things we have to generalize. So.
Okay, well, let's thank the speaker.